Okay, we are talking about authentic metrics and Laplacian metrics of graph G and their eigenvalue. And then we are exploring the meaning of them and how they are related to some graph theory concept. So another information about the graph that we can extract from the adjacency matrix are the number of walks. So if you have A and ij is 1, means that there exists an edge between I and j. What if we consider A square? You have a matrix A, and then you multiply it with itself. Then you consider ij entry. Then you can consider this as, say, all n, such that this is same as IL times LJ. And because this is either 1 or 0, and this multiplication is 1 only if they are both 1. And they are both 1 means that there is I and then there is L, there is C. Okay, technically, okay, you don't subtract it. So you know that this ij entry is same as this. Maybe let's write it this way. And what does this count? This is the number of walks from I to j of length 2. You can easily check that so A is the adjacency matrix. You can easily check that this KAIST power, and then you take the ijth entry, then that's the number of walks of length k, which is from I to j. So this shows that knowing the adjacency matrix, you can compute the number of walks between two vertices. And furthermore, using this, we can actually extract this information from eigenvalue. So for two vertices, we can find constant C1 to Cn, which depends on I and j, such that for all k, we have that for this, again, this is our adjacency matrix. The number of walks from I and 5 to j is you take the eigenvalue's power, and then you multiply with this constant Cn, and then you have, and you can obtain the number of walks from I to j, which has length k. So how do we prove it? If A is diagonalizable, we know that. There exists a matrix U such that U inverse AU is, say, D prime is a diagonal matrix. Moreover, this is a diagonal matrix with entries being its eigenvalue. And what? AK is from here, you just take the KAIST power, and then you multiply U on the left side, and then U inverse on the right side. You get this. Depending on the entries of U, we have that the k power on I and j are the U ij times mu to the k, and you inverses Lj entry over all choice level, and this proves, this number give you this number C. So we obtain the information about the number of walks from eigenvalue. Especially, if we take number of closed walks of length k, then from the above proof, you can check that so you have to compute the case where I and j are the same, and you do the computation, then we can check that this is the number of walks of length k, and then you can confirm that this is actually the trace. Same with the trace, and then that's the summation of KAIST power of eigenvalue. And from this, we can prove the following theorem. So what are the concepts related to number of walks? One of the very basic theorem that we prove is that a graph is bipartite if and only if it doesn't contain any odd walk, closed walk, or generally odd cycle. And that provides the following connection. We say it's spectrum. So these eigenvalues are called the collection of eigenvalues that are called the spectrum. This is symmetric. And this is bipartite, and if it is bipartite, this is symmetric, about 0. Meaning that mu1 is negative mu n, mu2 is negative mu n minus 1, and so on. So mu I is negative mu n plus 1 minus I. So we prove both direction. Assume G is bipartite. And let the bipartition be S and T. Let's assume that F is the first F number, T is the remaining numbers in bracket n. And what happened? And adjacent symmetric looks this way. This is symmetric, so, but what? First S number, there are no edges between, so this part is 0. And last n minus S number, there are no edges between, so this is 0. And this is symmetric, so this is B, and then B transpose. If you have a eigenvector with eigenvalue lambda, then what happens? For this one, let's say first X entries, you call it X, and the last two of them, you call it Y. Then you compute you multiply it with A, then that's same as lambda times is xy. But if you actually multiply here, then what you get? You get B, Y here, and then B transpose X here. Okay. Then what do we know? What we know is that instead of that, if you compute this instead, so here you have X, here you have minus Y, then what do you get? you simply put it here, then negative by, and that's b transpose x. And that's same as negative lambda times x negative y. So, hence this negative lambda is also an eigenvalue with the eigenvector x comma negative 1. Then what do we have? You write down the corresponding eigenvalues over here. And okay, so if you have one repeated eigenvalue, you take an eigenspace here, and then this argument said that you can find the eigenspaces for corresponding to the eigenvalue negative of that. Then you can check that these are all symmetric. So this is same as negative of this. The second one is same as negative of that. If there are repeated one, then the negative of that has to be repeated with the same number of times, because this shows that for eigenspace, you can find the eigenspace with the same dimension, which corresponds to the negative of this eigenvalue. So this shows that this direction. And for the other direction, and if the spectrum is symmetric, then for all both k, but we have that this summation of k's power of the lambda I is 0, because they cancel out. For odd k, lambda I, negative lambda I, if you take the k's power, they cancel out. Then, so there are no odd cycle. No odd walk. No odd crosswalk. So the graph is bipartite. In fact, you can prove stronger theorem. Here we assume that every spectrum is symmetric, then it is bipartite. But if your graphs verify just this, if your graph is connected and it satisfies just this, and you can show that it is bipartite. I will leave this as an exercise to you. You can try to prove it, but anyway, so we know this. So somehow, the eigenvalue contains information about whether the graph is bipartite or not. Okay. So now we are exploring various connections between the graph properties and this eigenvalue. And another one I want to present is about the clique number. So omega of G is the size of the largest clique, order of the largest clique in G. And then this is also related to the, to the spectrum. So what we want to show is that this is at least n over n minus u1. Then we later show that this will imply Turan's theorem. So this is stronger than Turan's theorem. So let's prove this. We want to first prove this theorem by Motzkin and Strauss. So let G be a graph with its largest clique at site R. Then the maximum over this is expression. For all of this, the one you take xy and then xj, and then multiply and add. It's over all non-negative vector x with the summation of its entry being 1 is this expression, half times 1 minus 1 over r. So we will prove this and then use this to prove this, and then we'll derive a Turan theorem using this. So, okay. So first, so we want to show that this equals to this, right? So this inequality is easy because this is about maximum. So you just choose one vector. Take the vector S being the, say, 1 over r times characteristic vector over u, where this u is the largest, one of the largest clique, then what? Then summation of ij in E of g, xi, xj is what? You just simply compute it, then you get that r cubed 2 over 1 over r squared, which is half times 1 over 1 over r. So you present one choice, and the left-hand side is maximum, so you get this equal. Let's prove the other way. So for other way, we write the port of x as the coordinate where it's the ith coordinate is not 0. This is the support of the vector. Then what? We want to show the following. Let's say we have an arbitrary non-negative vector x whose entry sums up to 1. Then we claim the following. There exists another non-negative vector y with y transpose a y is bigger than or equal to x transpose ax. So this is like the Rayleigh quotient without normalizing it, such that the port of y is a clique in G. So we claim that for any x, you can find such a y. And while you're doing that, this quadratic form does not decrease. Okay. So how do you do it? So you, for this x, let's say, if this x, the port of x is already a clique, then we are done. We just take y to be same as x. If the port of x is not a clique, then there exist I and j in support of x with this ij is not an edge. Then what do you get? Now you can write this down, this quadratic form is what? You take K and L, which are in here with edges, and you can categorize each term here, which contains xi and which contains xj. So for all the neighbors of I, you have term xi, xl. And for all neighbors of j, you have this term. And because ij are not adjacent, I mean, j doesn't appear here, I doesn't appear here. And the remaining ones, if KL is the edge of G, but ij is not there, G minus I and J. Okay. Now what? Here, ij is not an edge. So this is a linear function in terms of xi and a linear function in terms of xj. Let's consider each of these two as a variable, and then rest of them are constant. And this is a linear function. This is a linear function in terms of xi and xj, which are the variable for us. Then what do we know is that if you have a linear function, in order to maximize it or minimize it, the maximum or minimum appears on the boundary. When you have a linear function and you have certain variable, and the maximum or minimum always happen on the boundary. Using that, we can do the following. Let's just assume that this term is bigger than the other term. So let's say this term is A and this term is B, and let's say A is bigger than or equal to B. And what? Consider x prime be the vector such that if x prime's i's coordinate is xi coordinate plus xj coordinate, let's say L, if L is I, and 0 if L is J, and it's same otherwise. So simply you move all the values of xj to xi. You make xj 0, and then you increase xi using that, while keeping the sum of the all coordinate being still 1. Then what do we get? Is x prime, you consider this quadratic form in terms of this x prime transpose times A times x prime. Then you can see that this holds. It's simply, I mean, you just write down the all things here. Here this becomes 0, so this much is gone, and then here this becomes this plus x of j, so A times this much is increased. And this is increased amount, and then this is decreased amount. And this is what? By our assumption, A is bigger than B, you have this inequality. On the other hand, the support of x prime sheet, this is support of x minus j. And we can repeat this. As long as the support is not clicked. So in the end, we obtain vector y who supported the clique, and this value of this quadratic form is as large as the one for x. Okay, so now we prove this claim. Then what do we know? As this supports clique, so this has size at most r, because we assume that the largest clique in G has size r. Furthermore, again, this quadratic form is what? For all I in the support of y and for all j in the support of y, you add i's coordinate of y and then j's coordinate of y, and you multiply them and you add. This is same as you take all the support of y and then you add them and then square and then you subtract its term square. And we know that this is 1. So this is 1 minus summation of yi coordinate squared sum. But what do we know? We apply Cauchy-Schwarz. It implies that the summation of yi squared this is at least 1 over the size of support times the summation square. And what do we know? This is most r, and this is 1, so this is at least 1 over r. As you just plug that in, and this is at most 1 minus 1 over r. Then what do we know? That proves this theorem. Because here, this is what? For all h, you multiply, so xi, xj appear once. But on here, this you have xi, xj, and then xj, xi. So everything appears twice. So it's 2 times. So here we get the half of what we wrote here. So that proves it's Motzkin-Strauss. Okay, then what? From here, we know that by Perron-Frobenius, that we have this vector u1. This corresponds to the largest eigenvalue, the eigenvector. This is a positive vector. Then, by multiplying some constant if necessary, we assume that the sum of its coordinates is 1. So we normalize it. Then what? Using the Motzkin-Strauss, the mu1 times the norm of this vector squared is same as this quadratic form, and that's at most 1 minus 1 over the omega of G, Clique number. Then what? Using the Cauchy-Schwarz again. So this one is what? I's coordinate shared sum. Sorry. So here I have to go outside. 1 over n. Then what do we get? mu1 times 1 over n is n mod 1 minus 1 over omega of G. So omega of G is at least n over n minus mu1. So this is as desired. And then from here, what we know? 1 minus 1 over omega of G is at least mu1 times 1 over n. But what do we know? mu1 is at least the average degree, which is the twice times the number of edges divided by n. So from here, what do we know? The number of edges in G is at most half times this times n squared, which is the Turan theorem that we proved before. So using this, we can prove Turan theorem, and then this shows the relationship between mu1 and the Clique number of G as well. Okay, so today we talked about the relationship between eigenvalue of Alsace matrix of G and the number of walks in graph G. Using that, we proved that we can characterize bipartite graph using the eigenvalues. And also, we just show that the relationship between this largest eigenvalue and Clique number of G, and then using that, we can prove Turan theorem. Okay, next time we will talk about the relationship on independent set and chromatic number and eigenvalues of graph G. We will do that in next video. Okay, I will see you in next video then.